one of the normal themes that you will see in any conference on modern statistical mechanics is to have a very complex problem, like a problem dealing with sociology, dynamics of agents which are interacting on neurons or ecology. And then you're going to see models which are very simplified, like when you were describing the Ising model. So I wanted to dedicate part of this class to showing you to which degree even simple problems, normal forms, can be reasonable models for complex problems. So the theme of this talk is whether this. Big brother. So the topic is whether these tools are useful to describe real problems. So at the beginning of the first class, I played for you the song of a zebra finch. These are the zebra finches. These are songbirds which sing very simple songs. Well, very brief songs, I would say, not very simple. Why people study zebra finches is because they breed all year long. Instead of canaries, where you have to wait for a specific time of the year to breed, these breed all year long. And you would say, why would people study songbirds? Which is something that I asked myself, 20 years ago when I started, and it's because they are a great animal model to study how a brain reconfigures itself through learning in order to learn a very complex behavior, which is communication. So we as humans learn our vocalizations from listening to mom and dad, okay, and we start babbling and then we start talking, and that is not shared by many animals in the animal kingdom, by many species. There are some reports on bats or elephants and so on, but then you have a huge desert. Then you have ocine birds, which are like 30% of the known bird species, and they learn their vocalizations. So if you take a zebra finch and it's raised in isolation, it won't sing the typical song of the species. There are other species where that happens. If you deafen a pigeon when it's a baby, it will sing like a pigeon, but not for a zebra finch or a canary or for 40% of the bird species. So these are great animal models to study the onset of vocal communication. And people study their neuroscience, the biomechanics of bird sound production, and so on. So the typical song will be something like this. It will happen in less than a second. And you have all this succession of sounds. But these sounds are very different from each other. Some sounds, like this one in here, is harmonically very rich. What I'm displaying here is the frequency as a function of time. So what you do is you take your sound, and you do a spectral analysis by multiplying your sound signal by a little window, and then you do a spectral analysis, and you plot all the frequencies as a function of time. So whenever you have these multiple lines in here, you have that the sounds are spectrally very rich, like this thing in here. This is the sound trace, and this is the Fourier spectrum. You have all these harmonics. But then it interchanges those sounds with these sounds which are very, very pure. They are harmonically very pure. If you look at the time trace, they are like harmonic oscillations, and spectrally they have only one peak. So you have this alternation of sounds which are very rough and very tonal, and interchanges very much and very rapidly. And one of the questions that you have is whether this feature is controlled by the brain, and how is coded in the brain this very complex alternation between very rough sounds and very tonal sounds. But interestingly, if you look at the harmonic content, so this is an index that tells you how rich the spectrum is. If you look at the spectrum as a function of the fundamental frequency, what you have is that you have all these vocalizations that correspond to different syllables of different birds that were raised in different laboratories at different ages, and they place themselves, in something that can be described as a reasonably good fit, where the sounds with small fundamental frequency are harmonically very rich, and the sounds with a high fundamental frequency are very tonal. So the idea is whether that feature is something that is learned or is due to the biomechanics. And we have seen this in the first hour of our course, because I described to you one bifurcation that I call the saddle node in the limit cycle, the one that is described by this phase behavior, where you have that the solution of the dynamics can have no oscillations at all, but suddenly an oscillation is born with infinite period and a finite amplitude. And then if you change your parameters further, then you're going to have solutions that become more harmonic, because if omega is very large, then this term has no influence, and basically what you have is a harmonic solution. So as I described to you before, in this way of turning oscillations on, if you look at the scaling of the period as a function of the frequency, you can compute analytically very easily how the period scales with the frequency, and you can compute how the scaling goes. So interesting enough, if you go and in that normal form you study okay, I have it here. If you study the way in which the period scales and the spectral content scales for that bifurcation, you have this line that I have in here, where the only thing that I had to scale is the time scale, tau, of the oscillation. It's the only parameter you have to fit. So you have a very complex problem, which is a bird doing sounds with its seedings, and if you want to plot and fit all the possible relationships between the spectral content and the frequency, the normal form will fit it by just fitting the time scale. There is nothing else that you have to fit. How does it relate to the real equations of the problem? So this is the biomechanics of bird song production. Typically what you have is at the juncture between the bronchi and this trachea, you have this vocal device which is called the seedings. It has a pair of labia, very similar to the vocal folds that you have in your throat. You know? So when you make a voiced sounds like you have a vibration there. It's because you're sending air through the vocal folds and they start to oscillate. Well, they have two pairs of these. Okay? So if you model each labium as a spring with some restitution, okay, you can write Newton's equations for that. So this is Newton's equations for the midpoint position of a labium here. You have the elastic restitution of this tissue. You have some dissipation, some nonlinear dissipation that takes into account that it's a bounded motion between the lateral containers of the seedings and the labia themselves. And then you can compute, by doing some hydrodynamics, which is the average pressure in between the labia. And when you do that, you have two parameters, which is the air sac pressure that you have. So you have to build up pressure in order to send the airflow in between the labia, and the tension of the labia, which can be controlled by some huge muscles here, the syringelis ventralis. These are huge muscles that when they are contracted, they pull some rings that are sustaining the labia. So whenever these muscles are contracted, these labia are separated, and these labia, therefore, are more tense. And the fundamental frequency of those oscillations increases. So you have two parameters, the tension of the labia and the air sac pressure. And when you look at the bifurcation diagram, using the tools that I was describing before, you have a two-dimensional bifurcation diagram, like the one I was telling you before, where you have here the air sac pressure, here the tension, and here are the lines that separate the different numbers of periodic solutions. This red line indicates what is called a Hopf bifurcation. This is the way in which you turn oscillations on. We didn't have time to cover that in the first part of the course, but let me give you, since you were asking about complex solutions, a Hopf bifurcation is a bifurcation where the phase space is described by a complex variable, and then you have a cubic saturation term. So when the real part of mu is smaller than 0, then in your variables x and y, what you have is an attractive solution. And when mu is larger than 0, what you have is that you create a limit cycle like the one I was describing before. Okay? This is because when you write this in terms of an amplitude and a phase, this is going to be something like that. Okay? So this is going to be an homogeneous, monotonous increase in the phase, and the behavior of the radius depends. If mu is smaller than 0, all this is negative, and what you have is that rho dot is always smaller than 0. And if this is positive, then you will go to the rho equal to 1 fixed point that I was describing in the first hour. So this is called the Hopf bifurcation, and in our problem is represented by the red line that you have in this two-dimensional plot. So this is taking the real equations of the problem, the real equations, the ones that you derive from doing the biomechanics of a labium with air. It's a long exercise. But then if you look at the normal forms, by looking algorithmically to the simplest equation having the same linear part, then what you have is a bifurcation diagram that looks the same. Qualitatively, you have the same solutions. Now the equation looks much simpler because what you have is a term with no variables here, the linear part, the cubic part, and then you have some specific nonlinear terms. It is interesting, if you do the normal form, you know exactly what kind of nonlinear terms you can expect. And the only parameters are these and the time scale of the problem. So you go from a problem that's full of parameters, full of weird terms, and then you go to something that is polynomic and has only two terms, two parameters, and a scaling, time scaling, a constant here. And the dynamics is qualitatively the same. Everything here can be mapped to a solution in here. So this is a typical representation of a simple vector field with the same kind of dynamics. Now the question is how similar the solutions of these problems are to the real problems that in our case are the songs of birds. Let me tell you a little bit more about these parameters. If you want to test this model, actually the one with the real equations, you have to go beyond doing theory and you have to measure things. So this is the kind of things that we have to measure in the lab. These parameters are, as I said, the air sac pressure. So you measure the air sac pressure by inserting a cannula into the posterior air sacs, and then you connect it to a pressure transducer, which is basically a capacitor, which you connect to some voltage, and therefore when you have a fluctuation of pressure, you have a fluctuation in the distance of the capacitors, and therefore you translate the pressure into voltage. And therefore, when the bird is breathing, you have a small fluctuation. When the bird is singing, you have a huge fluctuation because it has to compress the air sacs a lot. The other thing that you have to measure is the tension of the labia, which we do by measuring the activity of the syringeal muscles that are controlling the seating. So here you have a syrinx, and these here are the syringalis ventralis muscles. So you have to do a surgery, which consists in opening the skin, opening the air sac, removing the fat, going to the muscle, removing the fascia, inserting the electrodes, fixing the electrodes, reconstituting the air sacs, putting back the fat, closing, sending the wires under the skin, and letting the bird want to sing to its girlfriend. It's a challenge, but if you do it fast enough and precise enough, you do it painlessly. It has a lot of protocols in order to do it without the bird suffering. And basically, the bird wakes up, and half an hour later, you put the girlfriend, it will look at her and start to sing. It's compulsive, okay? You present the female to the bird, and it will just start to sing. So when it does, when it begins to sing, the kind of records that you have is this. This is the sound. This is the pressure fluctuations. And these are the activities of the left and the right syringalis ventralis muscles. So here is a draw where you can see more precisely. This is the huge muscle, the syringalis ventralis. When this is contracted, the distance between these two rings increases, and then the labia, which are inside these tubes, get stretched, and therefore they start to vibrate at a higher frequency when the air goes in between them. So one thing that we used to do is to try to take the models, drive them with these parameters, and see that you have song. If you do that, but when you play the parameters in the normal form of the equations, you get these kind of synthetic sounds. So let me play to you the real sound and the sound that is generated by a normal form. So this is the birdsong song. Okay. Again, it's very brief. No one will study this bird if it wasn't that it breathes very easily in the lab. It's clear, right? It's a very, very simple. Okay. And this is the synthetic song generated by a normal form. So it's an equation that has only cubic terms and 2 quadratic terms. Let's see. Okay, so this is the normal form. And the idea is, okay, it sounds similar to us. The problem is whether for a bird it's similar or not. So what I'm going to show to you is a very nice experiment. Now, this movie is from like several years ago. Now our devices are much smaller, but this is what we used to do at the beginning. So this is a bird that is going to be singing awake. So the bird is actually singing, and you're going to listen to 2 sounds. One is the song, and the other one is going to be a because this is the neural activity of the brain, okay, which we're measuring the brain activity in a telencephalic nucleus, the high vocal center, it doesn't matter, and they were playing that time trace through a loudspeaker. So when the bird is singing, from time to time you will see that this sound, okay, gets interrupted and has some, temporal behavior, which is the way in which the brain is coding that sound. So let's see how that sounds. Neuron. Okay, when the bird is not singing, it's an homogeneous, and then gets modulated when the bird is singing. Okay, so now an interesting thing happens when the bird is sleeping. So when the bird is sleeping, this nucleus that we're studying is a nucleus that integrates the motor generation of the instruction of the gestures that are going to control the vocal organ with the auditory nuclei that are processing that. So when you play to these birds their own song, so what they were singing in the morning, you elicit the same response that the bird did when it was actually singing, okay? So you can induce in the brain the activity that is necessary to generate a song, but by playing the bird its own song. But you have to be very specific. You have to play its own song. If you play the song of a neighbor, of a tutor, of an animal that is living in the lab, it won't respond. It has to be its own song. So now we're going to see the bird sleeping, and when the bird is sleeping, we are going to be listening to a sound which is the recording of its own sound. Okay? Okay. And the rhythmic activity is exactly the same activity that it was recorded when the bird was actually doing the song. The bird has to be asleep. If the bird is wakes up, and we're going to be seeing the bird waking up, now there is no modulation. You play the song, and there is no modulation. But now it starts to fall back again, asleep, falling asleep. And now when the bird listens to the song, it starts to have the modulation of the activity. So what we did is the following. With Ana Amador, who is in charge of the electrophysiology in the lab now, what we did is the following. We play the bird its own song, and we recorded the activity. So in here what we have is the repetition of many experiments, like 20 experiments. Each point is a neuron, which is spiking, okay? So when you play the song, and the bird recognizes its own song, you have this burst of activity. And when you add all this activity together, okay, you have this big peak. Now, if you play the reverse song or the specific song, okay, what you have is basically no response. So let's play these songs. The bird's own song. Again. This is the same song backwards. That means you play, okay, when I was a teenager, we have the myth that if you play some records backwards, you will listen to the satanic messages and so on. Of course, I learned to speak backwards too. Makes great conversation anyways. But the idea is that if it's responding to some frequencies, okay, it will respond, but it doesn't, okay? It has to be the precise sound. And if you play a conspecific, it doesn't respond. So when we did this experiment for the first time, and I was in Chicago, in the laboratory of Dan Margoliouth, who is like a leading master in the field, and I was pushing this idea that if you do a normal form analysis, you will have a song that is so good that you could cheat a bird. So I went there, we set up the experiment. This guy is a big guy. So he generated this synthetic song, and we played it to a bird. And this is what we got. This is a disaster. Just to make it clear. There's no way of failing more miserably than this. Okay, it's not that you have some response, but it's tiny or small. There is nothing, right? Nothing. So I was pushing for many years already that biologists focus on details, and you had to, focus on the main mechanisms and so on, and then the bird does this to you, and you say that it's not fair, right? Let's play the song. Let's play the synthetic song. Tell me if this is fair. It is not, right? It is not. Anyways, so in physics, the problem that you have is that the good thing in physics is that if you do something in modeling and you're not being good enough, you know what you put under the rug, and you can work backwards and say, well, now I'm going to include this phenomenon, right? In biology or in agent dynamics or in many of the things that you do in statistical mechanics nowadays, you can't do that. The problems are very complex to do that. So there is no way in those cases to try to see what makes sense from the field itself. In my case, in this biological problem, the thing that I was focusing on was in the nonlinear aspect of the creation, and I was neglecting a little bit the filtering, because since it's a linear problem and it's not so sexy, I didn't pay too much attention. But basically, these birds put a lot of effort into modulation by the oropharyngeal cavity, which is an additional filter that you have. So without any indication whether that was what was missing or not, and maybe some noise in these parameters that I will explain to you why I decided to include them, we tried again. And so this is the experiment, including these factors. So again, this is the birds and song, the reverse, conspecific. And of course, I'm showing you this because it worked, right? The interesting thing is that for me, there is no difference whatsoever in between this simulation with the oropharyngeal cavity and not. But the birds are extremely sensitive to that aspect. So sensitive that if you do this experiment, you can find a very well-tuned curve of sensitivity to the different parameters of the problem. So here what I'm doing is generating a lot of songs where what I'm changing is the level of noise that I put in the parameters and the amount of dissipation that I have in the oropharyngeal cavity, which represents basically if I include it or not in the model. And I'm playing these different songs to the bird. And I don't know if you will agree with me, but to me they sound all the same. Well, but for the bird, there is a huge difference. And there is systematically, for all of them, some particular level of noise and some particular level of dissipation where you have the maximum. And this is independent of the individual and so on. And it's very interesting. If you start to play with the parameters, there are some parameters which are dramatically important for the bird, and other parameters that the bird doesn't care about, which I think is very interesting in order to study evolutionary why these parameters are going to be sensitive or not. That's a completely different set of stories. But the interesting thing is that you could generate this with a normal form. To have a bird which is completely picky about the sounds and yet being cheated by a sound source which is ruled by a normal form, which is a very simplified vector field. Okay, you were asking me about what happens when the dimensionality of the problem is larger. So what I'm showing you here, which we will need for what I'm going to be describing in a little bit more time, in a few minutes, what I'm showing you is this normal form, which corresponds to the Hopf bifurcation. This is the way in which you turn an oscillation on, and a periodic forcing. Okay, so this is the normal form that describes this, the appearance of a limit cycle. And this is a kicking, which is periodic. So this is the version, the nonlinear version of the exercise that you did in Physics 1 when you studied the forcing of the harmonic oscillator. So when you studied the forcing of the harmonic oscillator, you were in Physics 1, and you learned that when you have a harmonic oscillator with dissipation, you kick it periodically and you force it periodically, always you will find a solution with the forcing that is the forcing of the frequency, always. You put the ansatz, let's look at x equal to a cosine of omega t plus phi, and whatever omega, you will find the solutions. Of course, there will be amplitudes that the system prefers. This is the resonance. And there will be frequencies that were determined by the difference between the forcing frequency and the natural frequency of the problem. But basically, always you will find that the system gets entrained to the forcing. So a simple linear oscillator always surrogates its will to the forcing. The only freedom is the amplitude of the response, the resonance, right? Now, when you take a nonlinear system and you periodically force it, the dynamics is completely different. It is true that if you are close enough to the natural frequency of the system, you can lock it. And therefore, you can lock it if your forcing frequency is similar to the natural frequency of the system, you can lock it in a one-to-one solution. But you have many different behaviors if you start to departure from the natural frequency of the forcing. Let's see, all of us understand what I'm writing in here? Someone would like to stop here? Okay, one thing though, before I continue, why I say that this is a third-dimensional problem. So our idea is that we would have x dot equal y dot equal something like that. And then we have, I don't know, a periodic solution for the forcing. So this is a non-autonomous second-order differential equation. How can I drive it to a three-dimensional, to a set of ordinary differential equations? Well, what I can say, an autonomous set of differential equations, what I can say is that this is f0 cosine of phi, and say that phi dot is equal to omega. So I can turn a system which is periodically forced into a system that is autonomous by increasing the dimensionality in one. Okay? So in my problem, in the problem that I'm describing here with the kicking, what I have is the following. I have a system that would be described by a two-dimensional phase space, x and y. And naturally, if I have no forcing, okay, I would have that the system goes to a limit cycle. So this would happen with the system without the forcing. Now I'm going to be forcing it periodically. So that means that I'm going to be taking the time. But if I look at the period between 0 and t, I have that the vector field has different values. But then the system will repeat the vector field itself. So I can map everything that happens after this to this part of the phase space. Okay? Because the vector field will present nothing new after going to the time t. So in this system in particular, what I'm going to be doing is studying the phase space as a three-dimensional problem between 0 and t. And then I do modulus t, I go back here and keep on going. So a solution of period 1 will be something that starts in a point in phase space, does something, and returns to the same point in here, because this point gets mapped exactly into here. This is a period 1 solution. I have a time scale which is the period of the forcing, and I have a solution that has the same period as the forcing. But then I could have solutions that repeat themselves after 2 times of the kicking. So it will be something that starting here, goes back to a point in here, and then it will have to wait another time until it goes back to the initial point. That would be a solution of period 2. That means a solution that repeats itself, but after twice the period of the forcing. So what's the action of the last thing that I have to explain about this problem is what is the action of the kicking? Well, the kicking here is a delta function in the derivative by some complex number. That means that in the complex space, you will have a discrete jump of size epsilon each time that you kick it. Okay? So in here, what I'm doing is each time that system reaches a point t, I kick it, and the imaginary part of the solutions get a jump of size epsilon. If you do that, you can compute exactly how the system maps from this phase space to itself after a kick. Why? Because first, you know what happens in between the kickings. The system is evolving by these autonomous equations, and you can solve them analytically. Okay? And then when you reach before the next kick, the only thing that you do is that you jump in the imaginary part a size epsilon. It's a calculation, you have to do it, but it's nothing conceptually very complicated. When you do it, you end up having what is called a map. So a map is a description that instead of following the whole flow, tells you how you map the modulus and the phase in between kickings. So this is a 2-dimensional map. If the system is highly dissipative, you end up having what is called the Annals Map. Okay? But this allows you to study the system in between kicks. And this is the simplest kicking applied to the simplest equation for the limit cycle. When you study the solutions, as I was telling you before, you could have eventually solutions that repeat themselves after one kick. Okay? You are here, you kick it, you evolve monotonically, you go to the same point, and so on. These are solutions of period 1, and they live when the frequency, they can be found when the frequency of the forcing is very similar to the frequency of the natural frequency of the problem. And that happens, therefore, when the ratio between the natural frequency and the forcing frequency is close to 1. So here we have a period 1. But then, if you start to increase the forcing frequency, the system cannot catch up. So a nonlinear system is not so friendly as a linear system that will always surrender its will to the forcing, okay? It will rebel. So if you want to force it very fast, it won't follow you. It will wait to repeat itself twice the forcing. So this is what happens in here. You kick it, you go to this point, this is the same as this, then you kick it again, and then you find itself, the system finds itself in the original position. This happens in the parameter space close to the region where the forcing frequency is twice as high as the natural frequency of the problem. What happens when you increase the amplitude? The system becomes more complicated. Instead of repeating itself after 2 kicks, it repeats itself after 4 kicks, 8 kicks, 16 kicks, 32 kicks, infinite number of kicks, and the system is never periodic. This is what is called chaotic. So a very simple system, like a limit cycle, which is periodically forced, can become very complex and chaotic. And the question is every kind of system which you force completely different? No, they also come in flavors. They come in flavors. The flavor studied by Smale, the kind of flavor by Lorentz, and so on. You can classify these complex systems that happen in 3-dimensional dynamics. So let's again ask the birds how useful these low-dimensional models can be. So what I'm showing you here is the pressure patterns used by a canary when the canary is singing. So again, you have here the canary. In a backpack, it has a pressure transducer. has a cannula that goes to the air sacs that are in here. It's a thoracic air sac. And when the bird is not singing, you will have small fluctuations in here, okay, like at 3 hertz. But like here. But then when it starts to sing, it will have these jumps, and very fast it will generate these pressure fluctuations. Each time that you go above a threshold in these fluctuations, you have a sound that is generated. So the fluctuations that you have in here are not the sound. They are the fluctuations of the pressure. Once that you are with the pressure above a threshold, then you have the rapid fluctuations of the labia. So let's say that these fluctuations are like 300 milliseconds, okay? 50 milliseconds, but then the oscillations that you are having in the labia to generate the sound are like 1 kilohertz or 2 kilohertz. So the question that I have is, if this time series that is very complex, is generated by a brain that is activating a biomechanics and so on, can be described by simple models like the ones that I was showing to you before. And my faith and my prejudice is that yes. And here you have a very simple model of the respiratory system of a songbird that consists of an excitatory population and inhibitory population, which are typically generating a rhythmic activity for the respiration when you force it with instruction of the telencephalon in order to generate the pressure patterns of the song. So these excitatory and inhibitory populations are the ones that are tuned to generate a periodic activity. So, okay, when you have neurons, they can release some substance that will excite other neurons, and they are called excitatory. Or these neurons can release some substances that will inhibit the arousal of excitation in another neurons. The first class is called excitatory, the second one is inhibitory. And you can write a model for the average activity of a bunch of excitatory neurons, and you can write a model for the average activity of these inhibitory neurons. And normally, if you put them together, what will happen is that the excitatory will get excited, will excite the inhibitory, but when the inhibitory are turned on, they will silence the excitatory. And then, since they will have no longer excitation, they will go back, they will increase again, they will turn them on, they will turn them off, and then you will have that the normal dynamics of two populations of excitatory and inhibitory neurons are to generate some oscillation. And this is how the bird breathes. But when the bird wants to sing, it has to capture this respiratory system and generate some different patterns. So and that's what it does with telencephalic activity. It gets cortical activity and drives this respiratory nuclei here in order to try to engage them. So what I'm doing here is drawing a bifurcation diagram, a two-dimensional bifurcation diagram like the one I described before, for the behavior of an excitatory and inhibitory population of neurons. You have the bifurcation lines. Here you have saddle nodes, like the ones that we described in the first part of the class. Here you have Hopf bifurcations. And what I'm showing with arrows of different colors are the kind of perturbations in the parameters that I have to generate, that I have to apply to this system in order to generate syllables of these different kinds. So what I'm doing here is, for example, with the red, I'm doing this path in parameter space, and I'm changing the parameters and looking at which is the response of this system when you drive them periodically. And when you drive periodically this set of nuclei, what you get is this kind of solutions, which are like this. But what happens if you drive periodically, okay, in this region of parameter space? Well, what you get is this kind of solutions where you have a particular shape at a particular frequency. And then if you drive them right in here, you get this kind of solutions. If you look into the parameter space of the problem, of the forcing problem, for example, These solutions here are one flavor of period 1. These solutions here are another flavor of period 1. These are solutions of period 2. And if you look at the shape that those have, these are the first solutions of period 1. These are the second type of solutions of period 1. And these are the solutions of period 2. Okay? This is another subharmonic and so on. But the interesting thing is that you cannot tune these parameters to get whatever you want. Because going back to your question, if you go to some dimensionality, you go to dimensionality 3, each class of dynamical systems has a set of periodic solutions, which is topologically inequivalent to another one. So there is one family where you have solutions of period 1 of this type, and the solutions of period 2 will be to go close to one of the solutions and close to the other one, and will have a specific topological shape. And you cannot fake that. You cannot change your parameters and shape and adjust at the same time frequency and shape. You are restricted to some particular set of solutions. And therefore, the response is, can you model with one of these families of nonlinear systems something as complicated as the pressure patterns of a singing bird? And the answer is yes. So for next class, what I'm planning to do is to separate my lecture in two parts. One is the analytical tools that will allow you to show that a bunch of excitatory and inhibitory neurons will have this bifurcation diagram in parameter space. And I will show you how you take a bunch of excitable units, you couple them, and you have some order parameter that describes the average activity, whose parameters diagrams are exactly this. And the other thing that I want to show you is how we did in the lab to test this, okay, by manipulating the bird's brain. Okay, and that is all. That's where I'm going to stop today. So I'm going to continue on Wednesday. But the main theme of my class, I would like it to be that these very simple models that you're going to see in all these applications typically have a very strong mathematics behind that is not laziness of the modeler, but is the robustness of the normal forms that are implied. These agents are nonlinear, and basically they are paradigmatic and simple equations that are good models for the behavior of these units. So now I take questions.
When you bring out a bifurcation diagram that has two types of bifurcation diagram, like Hopf and
yes. Yeah, sudden node limit cycle, exactly.
That means that the normal form of the dynamics is a combination or a linear combination of the two types of
Okay. It's a very good question. So typically, what you do is you have one. Okay, so the first thing you should know is that the normal form is determined by the linear part of the differential equation. This is very interesting and very surprising. So the normal form consists on a systematic change of variables that will take your vector field and eliminate eventually the terms that can be eliminated through a nonlinear change of variables. But when you do that, you see that the fact that you can find a coefficient to eliminate the term depends only on the linear part of the differential equation. So the nonlinear normal form is determined only by the linear part of your differential equation. So you can ask yourself, what is your real problem? Well, if you know that you're changing only one parameter, typically the linear part will be the linear part of a one-dimensional system, and then you're going to be studying a one-dimensional bifurcation problem. But maybe you are interested in a problem where you can change two parameters, and you say, well, what happens if the linear part is very degenerate? So for example, in a two-dimensional problem, you could have a linear part which is highly degenerate. Why is highly degenerate in this case? Because it has two zero eigenvalues. Okay, so if you have a two-dimensional linear part, you could have a very simple problem where you have two eigenvalues, lambda 1 and lambda 2, okay? this would correspond to, for example, I don't know, one of the typical bifurcations in one variable and the other one. You can have something that has complex eigenvalues, like in the Hopf bifurcation, or you can have your third case, that is to have a double zero degeneracy. So this thing here is your third possibility. In 2 dimensions, there is nothing more. What happens in here? Depending on how you perturb it, you go to 2 real eigenvalues or 2 complex eigenvalues. So this one corresponds to having, typically, a point where a Hopf bifurcation and a saddle node collide, okay? And this degeneracy reflects the degeneracy of this linear part. So when in a 2-dimensional diagram, I say that there is a saddle node and a Hopf, typically what is happening, or what I'm cheating, or what I'm not telling you, is that I started this problem saying, I will take this 2-dimensional plot, and I will look which is the most degenerate point that I can find. So the most degenerate point that I can find is that I have 2 zero eigenvalues. And I take this point in here, and I start from there. And when I start from there, I say, well, I have a saddle node limit cycle, I have this Hopf bifurcation, and I start to build from there. So this point in here is what is called a Tagens-Bogdanov bifurcation, which is a bifurcation which is highly degenerate. And when you unfold it, you have all this richness of behavior. Yes.
So the question, I have a question is, did you actually observe such trajectories? And if you did, does this mean that the system about the bird sinking is non-conservative?
Okay. So I never found, okay, so I have it's a very good question, actually. Typically, the most complicated patterns that I found for these birds are subharmonic of up to period 4 or 5. I never found a really chaotic solution. On the other hand, these birds, what they generate are these trajectories, which are also very regular because the parameters are not fixed like in a lab, right? So all the parameters in biology are sort of more noisy, if you want. And it gets kind of complicated to distinguish between a chaotic solution and a solution where the noise is high, because we identify the same kind of periodic solution, and it's kind of complicated to really know that you're in a chaotic solution. So what I found is that for low periodic solutions, the organization in phase space is the one that you expect from one of these families of nonlinear systems. For example, if you take the period 1 that is small, the period 1 that is large, and the period which is a period 2, this family of dynamical system expects that you have a period 1 in phase space, that the period 2 links itself one around this periodic of period 1 and doesn't link around the second period 1 and so on. So I found many consistencies in the topology of the organization of the periodic solutions, but I could never prove that some solution which sounded kind of irregular was not a combination of these solutions with noise. So I owe you that. It's an interesting question, but I don't know if I could find it.
Have you tried to calculate numerically the Lyapunov exponents associated?
That's right. So the problem with Lyapunov exponents and so on is that these are methods which don't degrade gracefully with noise. So if you take a bunch of periodic solutions that live close in phase space and you put some noise in between them and you generate a complicated solution and you want to distinguish that from a real strange attractor that has those solutions as unstable solutions, then it gets complicated. That's the reason for which I prefer topological tests to periodic solutions and not, for example, Lyapunov exponents. So Lyapunov exponents degrade not so gracefully with noise. And the problem with biological systems is that you cannot control the amount of noise. It's very difficult to control the amount of noise. So for sure, if you take for one of those solutions and you compute the Lyapunov exponent, you will get signatures of chaos.
I mean, the picture you show in phase space, it looks chaotic.
It looks...
Weakly chaotic.
That's right. And I can show you one that is even worse. I mean, let me. If I plot you, for example, if I plot you in the phase space a bunch of songs and I play them all together, even adding the irregularities that you have in here, you will have the typical holes that you would expect in a weakly chaotic system. I mean, I can fool you with that for sure. I mean, I could publish that this is chaotic with no problem. I still wouldn't be convinced. Yeah. No, you're welcome. Herman.
I have a couple of questions. The first one is the basic one related to normal form. You said that it depends on the linear part of the linearization.
Yes.
So I guess that you have to linearize the equations with respect to a fixed point.
Exactly.
And how do you choose that fixed point?
So what you have to do is, well, you have to choose a fixed point that is pertinent for your problem. For example, in my case, it is the fixed point that describes the labia that are not moving. Okay, so you will have to start from a fixed point that makes sense in your problem. And then you take this fixed point, you linearize it, and then you look in the linearization which are the parameters that go to the kind of degeneracy that you want. Always a bifurcation is something that has eigenvalues with zero real part, so you have to look for the parameters that describe the regions where the eigenvalues of the linear part are zero, and then you have to identify the Jordan matrix that you have, where you have something which has complex eigenvalues, real and different eigenvalues, or one of them which is zero, or if you have two zero eigenvalues which are not the trivial all zero matrix. And then you start to build from there. But the fixed point is something that has to be pertinent for you. Normal forms are local techniques. Then you have to find a way of making sense of what happens when you start to study the whole nonlinear problem.
You use normal form for building the bifurcation diagram, and then there you go very far away from any.
Well, that's a good question, because when you do that, let me show you in this case in here, for example. Wow, we discussed a lot today. Okay, so here I started with a normal form around this degenerate point where you have a Hopf bifurcation and a saddle node in limit cycle. But then what I don't know at the beginning is how far I have to go in terms of the order of the nonlinear terms. So the normal form for something that linearly has this shape is something that in the quadratic terms will have terms that go like x squared or xy. That means that you know that you have something that is y squared or x squared or y squared or xy. In that one, you can eliminate them through some nonlinear change of variables. So you know that if you go to order 2, these are the only two terms you have to study. So I don't know if I'm clear, but you know that the linear part is this. Your linear part is this, and then you say, well, how many nonlinear terms I have to put? And then you can say, well, you have to put a square term like this, you have to put a square term like this, then you have to put a square term like this, a square term like this, or then you have to put a square like this or a square like this. I think I put them all. And you have to put parameters here, A1, A2, A3, A4, A5, so on. What the normal form theory says is that if you do that, you're wasting your life. Because through a nonlinear change of variables, you can eliminate this, you can eliminate this, you can eliminate this, you can eliminate this, and the only two terms that you have to keep are this and this. Everything else you can get rid of through nonlinear changes of variables. Now, your question is something quadratic good enough for your problem? And for my problem, it's not, because since I need to turn an oscillation on through a saddle node in limit cycle, this bifurcation that I described at the beginning, where you have two fixed points that are eliminated in a saddle node. Since I always have a fixed point in the middle, I need to have 3 fixed points in my problem. So in my problem, I know that I have to start in something very degenerate to have either saddle nodes and Hopf that determines which is my linear term in here. And then I know that I need at least 3 fixed points because I need one in the middle and these 2 that are the ones that are going to collide to generate the oscillation. So I need 3 fixed points. A quadratic term won't do it. So I know I have to go to the third order. If I go to the third order, the good news is that now it's the same. It's either x cubed or 0, or x cubed and 0, or x squared and 1. And now I won't worry you because it starts to scale a lot. Fortunately, the only ones I will have to keep are the ones that are 0, x cubed, or 0, x squared y. So I know that if I need 3 fixed points, and I want to start close to the degeneracy of a Hopf and a saddle node, I know that the equation has to be that. And I know it without doing a single calculation. I don't do a single change of variables from my original problem to this to know that my problem will be reflected by these equations. There is only one ambiguity, that is whether these coefficients will be plus or minus 1. This is too technical. But it's the only thing I have to study. Then, once I had a student that wanted to learn to do normal forms, and he did a PhD by showing that by doing these equations of the physical problem, how to do the computation of the normal form. Because he wouldn't believe it. But you can write this before doing a single calculation, knowing that you need 3 fixed points and the coexistence of a Hopf and a saddle node in limit cycle. Now, you want to do the real calculation, it's 3 years of work. But it's better to know nonlinear dynamics because you do it in 10 minutes, okay? So the only thing is that you need to know what you need. And in this case, it's cubic equations to know that you need 3 fixed points.
What you told us about the periodic forcing, with the deltas and all that. All the discussion about periodic forcing was regarding the state variables. But then at the end, in the phase diagram, you said that you move the parameter periodically. So that is another kind of periodic of forcing, I guess.
Yes, exactly.
How do you analyze that?
So, exactly. So in order to, in this case, I wrote this as an additive forcing to remind you of the kind of things that you did in Physics 1 when you force a simple oscillator. But the same philosophy could be whether you take here and you say, for example, that rho is rho 0 plus I cosine of omega t. You transform this problem into a 3-dimensional problem, and the only thing is that the way in which it enters is more complicated. So this is the only difference. The treatment is exactly the same. Now, to show that this system is mapped into one of the classes of systems that has some periodic chaotic behavior classified as the one we were discussing with him, this is a much more difficult problem. You have to build a map and show some features on the map that you derive. So for example, in this case in here that I was showing, the map you can show, it's a Smale horseshoe, and then everything that you study for the Smale horseshoe applies to this system. But it's not easy to do it from the equations themselves. You have to be able to build the map and study the features of the map. So you can classify them, but it's not as automatic as in the case of the normal forms. There is not the equivalent of a normal form for these chaotic flows. You have to study it at the level of the map, at least to my knowledge.
Hi. I think my question is like that. You have here parameters that depends on time. And you are saying that, if I understand, a low-dimensional model is good enough to reproduce that behavior. So why can you say that this time dependency doesn't increase the dimension of the model?
Okay, so the periodic forcing is increasing the dimension of the problem. If you have a parameter that depends periodically on time, then you increase the dimensionality of the problem. The only thing that here is kind of not obvious at the beginning is whether the description of having an intuition of the problem can be gained by looking at the two-dimensional problem and thinking that you change your parameters. That only works if the time scale of this changing the parameters is very slow compared to the time scales of the problem. No? So maybe that's where you're heading. Yeah. So that is completely true. This idea of gaining an intuition of the forced problem by looking at the autonomous bifurcation diagram and thinking that you change your parameters, it only will work if it's slower. If not, it's a completely different problem. It's the three-dimensional problem, and it has to be studied on its own. And the knowledge of the two-dimensional system and its bifurcation is not very helpful. Yeah, it's exactly right.
Thank you.
I have a question. This is a specific question about the experiment, not exactly the tools that you're using for analyzing your system. And it's about you remove theoretically the esophagus of the bird and then put it again, right?
No. The picture that I sent you was to show a vocal organ, so that was extracted from a dead bird. But typically what we do is with the bird with everything intact. You just open it, insert the electrodes, and close it, and you never extracted anything.
Because, okay, my question is if this kind of treatment cannot stress the bird.
Well,
and this stress maybe is going to the brain pattern, so you are modeling something that is not exactly the
exactly,
behavior
of course. So, of course. So what you do when you do the surgeries, and this is very typical. So if the surgery doesn't work well, so okay, basically what you have to do is to do these surgeries very rapid, very precise, and with a lot of care. If that happens, the bird recovers reasonably fast. And the way in which you test whether this went well or not is how similar the song is to what it was before you do the surgery. When you do the surgery sloppy, when a graduate student learns to do the surgery, and that's the first surgeries, then the bird doesn't really sing in the way it has to sing, and it has all these feedback mechanisms of trying to sing how it's supposed to sound, and it's a complete different problem. But the way in which you do it is by testing the behavior. So testing that the sound sounds exactly as it's supposed to sound. And this typically, if you do the surgery right, happens within the same day of the surgery.
Can be tested again, I don't know, a free period or something?
So we have lines of research. Okay, so yes. So some of this work we do them in the lab. Some of these works we do with Sabocin birds, because one of the things we're doing now, and I'm not going to be talking about this in the course, that's the reason I'm expanding that, we're using this activity in the masses to listen to what the birds are dreaming. So when the birds are dreaming, these patterns of activity go to the syringeal masses, and you can detect that activity and then play in the models, what these patterns of activity mean, and listen to what the bird is singing. So we're very interested in listening to the dreams of the birds that don't need to learn. So these are learners. We know that they have to practice at night. We know that they have a lot of brain activity where they're practicing their songs at night. But the question that we have is whether that is something that happens with the birds that learn to sing, or whether that happens to all birds. So there are all these species of birds which are called Sabocins. We don't need to learn, like João de Barro here for the Brazilians. These don't all the Quiscadí, okay, the bicho feo, venteveo. Those don't need to learn. So we test them what they are dreaming. So we do these surgeries in the field, and we study them in the field. And these birds are very high, they're very large, much larger than silver finches, and therefore every intervention there works better because they're less bothered. Okay, the electrodes are negligible compared to their masses and so on, and in those cases they behave normally and they are successful in the field, and and they have a normal life that you follow actually. Yeah. No, thank you.
A very small question about the first part about the biology and behavior of the birds. When you present the bird a different song from a different bird, maybe the female partner, what kind of response do you observe on the bird?
So what you're asking is when the bird is asleep and you play the, okay. So the first thing is that in this species, the birds don't sing. So in some species, they both sing, and that's an interesting experiment. But in this species, the females don't sing. And it's one of the lines of work that we're doing in the lab. What happens in the brain of a female bird, which is actually the one that makes the decision whether the song was good or not, right? Because it's ultimately up to the decision of the female to accept the copulation invitation by the male. So, but the bird, the male bird, doesn't receive an acoustic response from the female. So it's not used to the vocalizations of the female. The only thing that it can hear and respond to is the vocalizations of other males. When you play these songs, in this nucleus, there is no activity whatsoever. So this nucleus is a particular nucleus that receives input from the auditory system and is the one that generates the motor patterns of the generation of the song. There are other nuclei, which are auditory, which are responsive to the conspecific birds, to and so on, but we're not working with this. So in HVC, in this nucleus, this telencephalic nucleus that we measure, the only thing that the bird responds to is its own song. Okay.
Okay, let's finish.
So we'll meet after lunch for Mauro Copelli's set of lectures.
That's okay.
And
Yeah.
yes.
Get lunch.